Good morning. Thank you. Yeah, I'd like to talk about a topic that you probably don't talk about too much in spheres of this kind. This is about gravity. Relatively speaking, is a coarse resolution compared to imaging or altimetry or anything of that kind, or thermal measurements, for example. But it does have some possibilities, and I thought I would explain to you what has happened in the past and maybe where we're going in the future. The Forward on going forward. Hang on a moment. Let me understand. Okay, this is I'm going to be talking about gravity. This is the free air gravity model of 1200B, as we call it. And if you use gravity at all, then there's no letter B at the end, or A or C, as the case may be, is kind of important if you're interested in the shorter wavelengths. It refers to a constraint that's applied in the recovery of the gravity field in terms of whether it's tied to push the higher coefficients towards zero or push them towards the topography. All sorts of things can be done there. So you need to be careful at this. I happen to use 1200B because it's unconstrained most of the time, except at the very high wavelengths, or short wavelengths, I should say, where it is pushed towards zero unless there's a signal. So the gravity field of the moon has, thanks to GRAIL, which was a two-spacecraft mission that chased each other around the moon for a total of no more than about a year. But actually, there was only 6 months of data. In the first 3 months, planned this way, by the way, it was at an average altitude, periapse altitude, about 25 kilometers. And in the second 3 months, it was at an average altitude of about 25 kilometers, at about 15 kilometers. So we really got quite high resolution. And when you think about dividing the altitude by about a factor 2, gives you a spatial resolution. So on your 15 kilometers, you can probably get spatial resolutions horizontally of about 7 kilometers. So that's what we're talking about here. Nothing like we can get in imaging, but on the other hand, it does have some relevance, I believe, to understanding the deep interior as well as the shallow interior, for that matter. So let me move along to the next. Okay, the first comment I want to make up is that we talk about is we forget sometimes that a gravity field of a good quality gravity field can be extremely helpful to all sorts of missions. And this shows here, this is actually for the Lunar Reconnaissance Orbiter mission. It shows what the improvement was for using the GRAIL gravity model compared to what was available prior to that. And if I can make this work. No, wrong one. Hang on a moment. Am I going the right way? I'm doing really well here, aren't I? Oh, I've lost. Oh, there's something wrong there. Anyway, never mind. Can you move me back to slide? Okay, thank you. Appreciate it. Yes. This is on the right-hand side here. You see the comparisons of earlier gravity fields for the orbit of LRO. And just look at the bottom ones of the groups of 3 here. You'll see that, in particular, if you look at the elevation one, or the radial, which is the second one up from the bottom down here, you'll see this quickly line along there, pretty constant all the way across at about 10, 20 centimeters radial accuracy or something like from the gravity field, but consistent all the time. If you go to because of the logarithmic scale, to get any of the others, we're getting up to numbers that might be many, many meters, for example. And that's not too good if you're trying to measure the topography of the planet. So GRAIL has helped immensely. But we've redone the gravity fields of Selene, Chandrayaan. Chandrayaan was done for the benefit of the M-cube data, for example, because it would have benefited from the improved resolution horizontally and radially. And we've done many other satellites as well that are for purposes that we needed. Okay, and so it's helped in many ways at all. So for gravity field modeling, topography is for orbit determination. Gravity field work has provided quite an improvement in the fields, and it's been very essential, actually. And in fact, It's enabled us to do things like with the topography, getting out a very good resolution fields and so on, but also to which all the imaging data is rectified right now. So because of the improved resolution of all these things, all the LROC data is tied to the same field as the lower altimeter data, which is tied back into the whole system of including the lunar and the lunar laser ranging data. So let me move on here to the next chart. Okay, this is just some examples of the things that you've seen and you use in the gravity in some form or other. And you'll see here, and I don't really have a chance to go through them all, but you'll see some of the pictures that you've probably seen from Mach-Wizorek, for example, on the crustal density and how it varies with potentially with depth, what the mean porosity is like, what images look like of the gravity field down on the bottom here. Oh, got it. And the bottom left-hand corner over here of imaging by Greg Newman of what the gravity field looks like on Oriental. You see the far right-hand side here, the work of Andrews Hanna, for example, who found by looking at the gravity field was able to find linear features, for example, in the gravity field that are just not evident in the topography. You can't see them at all, but the belief is that they represent dikes that were formed maybe 3 or 4 billion years ago, actually, when the Earth was being formed, and there's still evidence of those dikes around here, and they're very linear, which is kind of surprising, so very different from what we would normally expect to see. So let me move on to this. I wanted to talk about the radial spectra of gravity. You don't think about spectra of gravity, but if you look at if you determine a gravity field, it's composed of circle harmonic coefficients from, in this case, 1200, that's where the 1200 comes from, down to about 2, which is the deep interior, almost the shape of the planet, not quite deep inside. And then 1200 is up really near the crust, I think at about a few kilometers below the crust. And so you can look on the left-hand side over here, and we've done these for the various sites for the Artemis site. And this is Apollo, you probably can't read it, but just looks like a quiggly line down here. And Crisium is very similar, although it's a little bit more, I would call, powerful down here. And it's the same with this one, Dirichlet-Jackson on the far side. Again, it just looks like a wiggly line. But if you want to know what the gravity field at the surface is, we naturally and do integrate through these coefficients. And you don't see that happen, but that's how it's done when you look at a gravity map, as we did on the first chart. And I've done that for these three over here, just as examples. And when you integrate from the bottom upwards, you see in this particular case for Apollo, it comes up like this, reaches a maximum here and goes up and stays pretty stable there. The point about this is that there's a location in this particular case around here, which is about L equals 60, which suggests which is where, in fact, most of the signal associated with that you see at the surface comes from. It's coming from degrees in that 55 to 60. And if you can interpret that in terms of depth, and you can to some degree with regard to certain models, for example, then you find that this is occurring at about 30 kilometers below the surface, quite close, actually, closer than you might anticipate. And you can do this for all of them. And it's not just quite the actual values themselves, it's how they change as you move across the lunar surface. So this is Crisium. Crisium is actually probably an older crater, and it's down here in, it looks like about 75, 80 kilometers depth, but it has a very clear maximum, as you see here. So I wanted to use that, and we have used it to look at the underneath major basins. So you can see something about the depth of these things. And we're talking in the first few hundred kilometers. And then I want to look at the polar regions, for example, which are in the shallow regions. And I'll come back to that in a moment. And the shallow regions are right at the top up here. Okay, this is the bad part in some senses. Okay. Okay. This is on the top there, looking from left to right, you see a profile on 266 east of the gravity field through Oriental, right through Mendel-Rydberg, up down to the South Pole itself. So this is the equator down to about 70 south. And if you look at what the This is the image here. But if you look at the spectra, which are shown underneath here, according to the latitudes along here, you see, you're starting off at the equator. This kind of the pattern is seen here, fairly straight. Nothing happened very much. When you move into the region of the where the shallow part is, or if you like, the dikes and so on around the anomaly, then you see it lie, and it slowly creeps up higher as you get towards the middle. And then when you get to the middle, the peak of this goes slowly down until it gets down to about here, which is actually almost a negative value. And then when you get in the middle between here, it's fairly straight, not too active, but there's no real pattern to it except, okay. And then when you move into Mendel-Rydberg, you see the same thing here. As it moves full into the high region here, you see the peaks appearing here and appearing here. And as you move out, peaks go down again. And when you get to nearly to about 70 north, you see the strait here, yes, and there are some trends here, etc. But the point I wanted to make here is that in places like Oriental here, you see these peaks are occurring at about this region here. This is about L equals, I think it's about 70 or 80 or something like that. And that corresponds to approximate depth to about 50 kilometers. And if you look at where the peaks are coming from for Mendel-Rydberg, they're coming from about 32 kilometers. It doesn't say what the peaks are caused by, the density differences, of course, but what they're caused by, we don't know. So you can use the gravity field to kind of infer something about things at modest depths. And the last thing on this chart, I would say, is that you notice that all these things come together about down here at degree in order 20, which is probably 150 kilometers or something like that region. Okay, and that suggests that the effect of any anomaly you see at the surface in this particular case, and these are big anomalies, you don't see them down at below 100, 200 kilometers, say, or something like that. They're gone. What you see is something else, but you don't see really those anomalies themselves. So let me move on now to the other part of the thing I wanted to show you. This is the polar regions. You've seen pictures of like that today, and on the left is the topography, and you'll see 13 black dots, which are the Artemis sites. You also see 4 white dots, which are 4 permanent PSRs that we've chosen to have a look at as well for comparison purposes. And you can see on the right-hand chart, this is the gravity field, and it's in a limited degree of 270 to 700. Don't worry too much about that, but it represents the top, say, 15 kilometers of the crust. Maybe a little less, but it's that sort of what it's right at the very top. It's the area that we are cautious about normally, and would be for many parts of the moon, but in the polar regions we don't have to be. And the reason for that is that there's so many tracks of the gravity field across the polar regions are so great that the quality of the data is really very good. Thank you. So this is what the gravity field looks like here, and if you go to close-ups here, you can see that the spots lie in certain high elevation places, including the one we've just heard about, which is the one on the very high regions, about six kilometers above the mean surface. So let me move on. Okay, so if you look at the spectra now, we're dealing with a very limited range of spectra now, from about 1200 down to 300 or something. But you see the wiggles are up here, which we don't really understand at the moment. Okay, so the solutions I'm going to show you for the density are from 2 kilometers to 5 kilometers. And we get that by minimizing the variations along the profiles here, the vertical spectra, I should say, really, to come up with the density. And the words are on the right-hand side here. But that can provide you with an estimate of what the density looks like. So if we go to the next chart, then these are the densities that we see. And it's interesting because the average is about what you expect for the planet, okay? That's what was about 2,500, 2,550 or something like that. Okay, and over here you see the first 3 that I showed on the other charts, and over here the 3 PSRs. But the thing about this I wanted to bring out is that this is Horwath. This is one of the sites, and this is a Horwath PSR. The difference between them is probably 50 or 60 kilometers. They're not far apart. However, they are 6 kilometers apart in elevation, which might account for this. We don't know at the present time. It's very difficult to calculate this precisely and be sure that you haven't corrupted the data from things that are surrounding it. But this is what we're beginning to see, and the variations around here are quite large, from the high of Horwath, actually in the high of Horwath and the low of Horwath associated with the PSRs. So you can get out the density in these areas, or you think you have, and I hope we've got it right. I can't prove that. And it only gets you to within about 2 kilometers of the surface. It's not like, it's not really useful in terms of a scoop or anything like that. But if you're thinking about long-term mining or anything like that, that's probably a depth that might be reasonable. Might be, I don't know. And certainly it's something that we're going to work on to try and get closer to the surface. But the limitation of the gravity field is probably a kilometer or something like that. And we won't get better until we're on the surface, can make gravity measurements there that will help us interpret what they are like. So the last chart is just a summary of what I've said here. GRAIL has provided this high resolution gravity. Lowell provided the high resolution and high accuracy topography. You put the two together, and this gives you the kind of resolution we've seen here. And one of the only lots of comments, I would say one of the things that we found out very early on was that the thickness of the crust is only about 75% of what we thought it was going to be. So it's more like, on average, 35 kilometers instead of 45 kilometers, give or take. Thank you. That's it. Thank you.